Good evening, ladies and gentlemen. Welcome to the 907th meeting of the Amateur Telescope Makers of Boston. Hoping you're here to safe ride in. In case I forget to say at the end, drive back very carefully. There's a little bit of snow coming in on Route 2 and I was driving in. We'll start with our committee reports. By the way, that is a mistake. Bruce did the refreshments last month, and we had a quick change, so I'm doing the refreshments this time around. So if you have any complaints, just see me and we'll take care of it. What's that? Well, that was one of the things. That's on the menu, my head on a platter. We'll start with the Secretary's report, Phil Levine.
I'm going to read a summary of the ATMoB meeting held February 8th here at the Smithsonian Center for Astrophysics in the Phillips Auditorium. President Glenn Chappell called the meeting to order at 8 p.m. Please see the newsletter for details on the Secretary report, Treasurer's report, membership report, observing and Clubhouse report. Announcements. There's been a recent establishment of a mirror and telescope making committee and also an outreach committee. Under announcements, the following board positions will be open after the current term expires: Club President, Club Vice President, and Club Secretary. Mario Mata made some announcements regarding light pollution. He mentioned that there's an establishment of a Massachusetts chapter of the IDA, International Dark Sky Association. And on February 14th, Mario was involved in a debate out in California about LED lighting. I think he's going to say more about that later on. John Sheff informed the membership about the upcoming Cambridge Science Festival, which will be April 13th to 22nd. Old business none, new business none. The guest speaker for the evening was Kevin Collins. His talk was about the 2017 total solar eclipse and was titled Journey into Totality. Kevin outlined the logistical issues involved with proactively selecting the best observing site for the 2017 total solar eclipse. He utilized different weather prediction online resources in order to get the best picture of the clearest weather. Kevin presented various impressive photos of totality, and Glenn Chappell adjourned the meeting at 9:35.
Okay, observing committee. I know I do this every year. Poor Bruce, I put it down.
Take my picture off of there, will you? He puts the observing report together, puts my picture up there, but doesn't share it with me until the meeting
Well,
right
if
now.
my picture's there, it would scare everybody out of the room, at least. But seriously, and I want to mention this now. We have two new committees, and I love doing the OC reports, the observing committee reports, but I don't want to take away from these other committees. They deserve their amount of time too. So I may kind of cut back on this and just have the picture, and we'll talk about the different things that are going on. It'll be in the newsletter anyway, so just to kind of save some time. But what we have going on this month, on the 15th, Mercury will be at its greatest eastern or evening elongation. It's actually pretty favorable one this time around. Mercury will still be low. You want a good low western horizon, but you will see it'll be paired up with Venus as well. But they're both very low, and they're about the only planets really that are readily visible in the evening sky.
Excuse me, I'm sorry, but you have up at the top March 8th to April 12th, and your first event is outside of that
Oh, I don't know,
time
yeah.
period. So are they March or are they April?
You know what? This is a problem when I'm getting things ahead of time. So the dates are wrong. So everything else is okay.
Which date?
I do.
Is it March 15th?
I got confused the last time. Let me think about it. These are all
Come with age.
today, March.
We're in March now.
Ignore that. I'll put something in the. I think what I did was I had it already done, and then I went ahead and changed it for the next month. I'm a month ahead of things. Last month I was a month behind. Yes.
Did you maybe just switch April and March?
I think so.
I think March 15th and April and March 28th, and then April 2nd and April 7th?
I think you are right. I apologize.
Well, the bottom line,
Yeah, I think these should be down. I'm right, that's what I did wrong. These should be down more because Mercury will be the greatest evening elongation next month. This is the key right here, and it'll be the end of the
No,
month. But I will go home
March
and check out and
15th is
get this
No,
straightened.
Actually, March 15th is the greatest elongation.
All right, March 15th, you got it right there?
And March 28th is the Venus-Uranus conjunction.
Yeah.
So these should read March.
And those.
These should read April.
I was gonna say, the bottom line is just go out there and look at Mercury.
Exactly.
Because it's really pretty in the sky right now.
So it would be March 28th, am I right? Thank you, John. It's a good thing you're here to straighten things out. This is key. These two planets are going to be literally be like a double star. They're only going to be about 4 arc minutes apart. The problem is, this is very low in the sky. They're talking about this being a telescopic event. You might even have trouble with binoculars because Venus is so bright. So I apologize for today. These should both read March, and this should read April, correct?
Yes.
Okay. As far as April goes, there are a couple of conjunctions with Mars and Saturn and the Moon. Those occur early in the month, but I think these are the keys right up here. March 15th, March 28th, and that's the one that you really want to key in if you have a telescope. That should be that's going to be one of the closest conjunctions of those planets ever. So you can see them both in the same low-powered telescopic field, but Uranus is going to be hard to see because Venus will be 1,000 times brighter. Sorry about those dates. As far as the challenges, observers' challenge for March, the LVAS came up with a double-lobed planetary in Gemini. It's not the ATMoB down here, it's 2371-2 up here. It is a double-lobed planetary nebula, about 11th magnitude. So give that one a shot if you're going to be out at the clubhouse doing some observing. That'll be a target. The Sue French Fan Club, her March column is about the crab and the water monkey, Hydra. And she had a bunch of objects there to pick out. And I decided she had a beehive M44. And if you're a newbie, try that one. That's an easy one. You can see it with the naked eye throughout the country. It's a nice binocular sight. But I wanted to go a little bit more and try Messier 67, M67, which is a very rich cluster not too far from Alpha Cancri. So give that one a look-see this month as well. And finally, as far as observer, yes.
I gotta add a couple of things before we get too far away from it.
Okay.
So I have a couple of, so I'm with Bruce on the observing committee. I'm Rich Nugent, by the way. Couple of extra things to add here before we get too far away from observing. This month, Humanity's Star, the New Zealand geodesic little reflecting light pollution-y satellite, is going to start making nice passes over North America. So this would be the time to go out and look for that if we ever get any clear skies. The other thing that to pay attention to satellites this month is the Tiangong Chinese space station is expected to re-enter sometime during March. And it's inclined about 43 degrees to the equator, which means that every now and again, like, passes over New England. So that might be fun to watch for. Heavens, did I say watch for or watch out for? Watch out for. Heavens Above is a good website for satellite predictions. But you can get some really up-to-the new information every day on the skyandtelescope.com website and astronomy.com website. Those are pretty good. You know, going back to that LVAS thing for a second, you guys should try and get out there and look at these things. Some of them are actually easier to see. They're harder to find than they are to see. Sometimes getting onto the star field is the hard part, but if you get a good atlas, you should be able to go out there and do it. That 2371-2 is actually a pretty easy object to find. I was looking at it just the other night. It's small. It's Jupiter-sized in the sky. So to give you some idea, you know, that's tiny, about an arc minute across. So you want to use as much magnification as the night will hold. I found that a UHC filter helped pretty much with that one a lot. The Oxy 3 was a little bit too much filter for my 10-inch scope. You know, I swear you need a bigger telescope to drive light through the oxygen filter to see it. But it looked pretty good with the UHC. Could you go back to that slide for a second? Oh, there it is.
Get it already.
This is the southwestern lobe right here. And that central star is 14.8 magnitude. That's pretty faint. That's hard. But what I noticed in my 10-inch was that this bright spot right here, when the seeing snapped up, it actually looked almost star-like. And I went on the internet the next morning, and I found a Hubble image that shows it to be a jet actually emanating out of that system. So it's actually pretty cool to see. And it holds up well with the UHC filter. It's not a star. It's actually part of the nebulosity. It's actually kind of cool to be able to see that.
You're not going to see the lobes naked eye though, are you? is in the picture, as in that picture?
My impression of it in the 10-inch at lower powers
Yeah.
was that it looked like a little version of M76.
Did you talk, you're meaning these right here, Bruce?
Yeah.
Yeah, those aren't visible, those are, but
Oh,
this is what you would see right in here.
Right, okay.
These extensions
Yeah.
are, if you read, let's see, I was looking at one of the Sky and Tel books on it, one of O'Meara's books, and they talked about seeing those in very, very large telescopes. I saw no hint of these little extensions here, but the double lobe nature of it is pretty apparent. And so that's something to go out and look at. If you've never seen it before, go find it. It's actually pretty easy to find. And, you know, I don't think you'll be disappointed. Just one more thing to mention about the LVAS. Not that I'm taking over the show here.
That's okay.
The February report was on Messier number 41. And Roger Iverser published that, I think it was yesterday, or perhaps the day before. ATMoB members provided almost 50% of the reports for that edition of the report. So nice job, you guys. We're the major contributors for that. So that's pretty cool. And yeah, that's pretty good. Well, that's all I want to say about that. You should go and look at that. That's pretty cool. You should go see it. It's your homework.
Oh. At least you get the dates and things right. We should have to do this more often, I think. Anyway, that's the target for from Sue French's article. And what happened was Paul Villoli, this was last month, he had suggested a couple of deep sky objects, but it was preempted. Who did? Was it you, Rich, that did the ones last? Oh, Joe.
I think I did.
Rothschild, yeah, Joe Rothschild did some last month. And Paul had suggested a few, and I kind of combined Paul with Roger Iverson through and something. There's so much about Roger, that's his picture.
Which one of them is which?
We'll have you stand right up here and you can see it up close. Good picture of Paul, by the way. Anyway, two things. Paul had mentioned the Horsehead Nebula, which would be a challenge. It's not going to be very easy. I don't know, has anybody seen it from the clubhouse, Steve? You think the 25-inch? With an H-beta filter?
I can see with the 32, but you need an H-beta filter.
Yeah.
It's really faint.
Because the only time I saw it was with an H-beta, was with a 17-inch.
And Mario, you have pretty good skies, right? You have pretty dark skies?
5.5.
Yeah, it's pretty good.
Well, ours are what, about approximately 5. The thing is, a lot of people don't realize this is tiny. I mean, I put the picture I chose shows the whole belt of Orion, so you can see the size. It's just that little indentation right there. In fact, with a 17-inch, all I saw was an indentation. I didn't see a horse's head at all. So that's a definitely tough target challenge. The other one is the trapezium, Iota 1 Orionis, and it's in the Orion Nebula itself. And with a small aperture scope, you see the 4 stars, the main ones, A, B, C, and D. I think with a 13-inch scope that I sold Bruce, I stopped it down to 5 inches and I was able to see the E and F stars. So you can pick out 6. As far as the other ones, you know, it's a challenge, larger aperture by larger aperture. How many of these stars in this multiple star can you see? So that's a nice challenge. If the seeing is pretty steady for you, and you see the Orion Nebula.
Why would you stop it down? Because the nebula is so bright? Or?
No, what it is with that big scope, it's a light bucket, and the imaging isn't that good. You know, it's very lousy resolution. So when you stop it down, it turns it, and this is a while ago, and it turns it from a 13-inch f4.5 to a 5-inch f10, I think it was, a 5-inch f12. Boy, what a difference. I looked at Castor one time with that scope, it was like this. Then I put that aperture mask on, it was like 2 nice sharp images. I was getting down to about 1 arcsecond with that scope using that mask. So that's the key. Sometimes with these large light buckets, if you make a mask for them, an off-axis mask, you avoid all those problems. Okay. Any questions, any suggestions, any additions? Outside of me getting the month of the year straight next time around. Okay. Steve, Clubhouse Report.
Well, we've had a fairly busy month. Our work party in February is in the Bulletin in Starfields, and we also had one on Saturday, March 3rd. And by the way, we have a second work party in March on the 31st, so it's kind of a blue moon work parties. We have a pair. We had done some basement work this past month. I think I mentioned last month the heating system was a problem, and we got that fixed most of the way. We still have the heat shut off, and we have very, very cold air in the stack, but we'll continue to troubleshoot that. But I'd like to thank Vladislav, Mitch, and Hugo and
Milch.
Diego.
By the way, it's Milch, M-L-C-H.
Okay, well, we call him Slav. Right, Slav? Yeah. Okay, Slav. And Hugo and Diego Alvarez, who also helped out in the basement and helped organize a lot of stuff. Something we talk about doing every month, but it's like it's put off. Anyway, they really took the bull by the horns. We also cleaned out the evaporator room and made room for a couple of more telescopes, which we will be getting. And also, we did some work on the roll-off roof observatory. John Marr had purchased a moonlight focuser for the 16-inch from Clubhouse funds and installed it, and it works very, very well. Dave Prouton also did some work on the 25-inch job. He reset the focuser, and then Phil Brownsville was able to collimate the telescope, and it holds. It's done very well. And he also had reconstructed an electrical box to plug in the heating elements for the 25-inch. And this relates to what Glenn and Rich were talking about, NGC 2371-2. If you look at a planetary like that in a big telescope under high magnification, you really see detail in it, especially when the scene's good. And also, another tip when you're looking at faint fuzzies, wait until they're on the meridian, when they're at their highest point in the sky. Looking at anything low is really tough. And I think that's part of the problem of not being able to see the Horsehead visually, even with an H-beta filter. If we were about 20 degrees south of here,
I see it from Westford.
you can see it when it's
But-
good and transparent.
But, yeah, you're right. The highest point is best,
Right.
but I still need an H-beta filter.
Right. So just for an experiment some night, go out and look at a galaxy or a planetary when it's fairly low. And if you're around 2 or 3 hours later when it's higher up, take a look at it again. Same sky conditions, same telescope, you'll see an enormous difference in the image quality. Back to the clubhouse. This.
Don't bump.
Oh, yeah. We're getting a much more active mirror-making group these days. Mike Maddy was the impetus for this, and I want to thank Tom McDonough for carrying the ball on this as well, and a member, Barry Jensen, who I don't know very well, but he's a real go-getter. We want to make an investment in the mirror-making activities at the clubhouse, possibly construct an auto collimator with one of the 16-inch flats that we have. It's been tested. I think Phil told me it needs about 200 strokes lapped.
I need about, it's gonna need a lot of some hand figuring.
Some hand figuring, which he volunteered to do for us. And we'll get somebody to cut the hole in it as well, a 2-inch hole in the center down the road. But we'd like to do that, and we'd like to also kind of reinvest in the grinding machines and the polishing equipment and bring that up to speed. I think we'll garner a lot more interest in the mirror-making activities this year if we do that. So stay tuned. Also, we have a...
I think I've heard a rumor that we have about 10 people working on mirrors now.
10 people?
So it's a big uptick from what
Yep. Yeah, that'll hold them if we can get this stuff going. Absolutely. We have an abundance of telescopes at the clubhouse still. About 4 years ago, we did an inventory and there were 50. We're now down to 45, but I know of 2 more new arrivals. So we're pretty much back to square one. So there's been a lot of impetus to move some merchandise and in the process maybe even make a little bit of money. So again, thanks to Tom McDonough and Bernie Kosicki for taking the lead on this, and Maria Batista, who also added a feature to our website where we can now bid on a telescope. And hopefully each month we'll add a new telescope to the website that people can bid on it. And I don't know if they can call it up right now, but we have a 10-inch mead, a DS10, a German Equatorial f4.5 that's in very good shape. And the starting bid is only $75. It is a steal. The finder itself is new, and that was $100.
This is the old,
So,
the old meat, okay.
yeah, it's a mead. It's the old DS series that mead used to make. It was, yeah. And one fellow who used to be in the club actually put some money into it. So it works.
Yeah.
It's a great deal.
We can bring it up if you like.
Oh, anybody want to take the lead here? Mind if we take a quick minute?
You might, yes. Just
Just don't screw up the date.
Or the amount.
Since we started the conversation, the telescope is now up to $100.
100 already, wow. And this is all money going to the club incidentally. Okay, member login, and then we go in under,
Yeah, so after you log into your account, it's in the, you go to the member, oops, sorry about that. It's telescopes up for bid.
there it is. And we have a picture of it too, no?
Yeah. So you can download a file with the information of the telescope. Now, this is a manual process, so this is not automatic bidding. Please read the rules and all the information before putting any bids in.
There it is.
Yeah, I'm pretty sure I picked that up at somebody's house.
$75.
Yeah.
Wow.
Starting bid 75. Yeah, we hope to get a little more. Yeah, it's fully operational, except it does not have a Telrad, it has a Telrad base. But a 9x50 Orion finder, that retails for $90.
How long are things gonna be up for grabs? I mean,
Until 21st.
oh,
Yeah, the 21st, right?
Yep.
Where's the show?
So you have the starting bid right here. You have the end date. When Bernie updates the website, if someone has bid on it, you'll see the updated bid amount. And he'll also post the date that it was bid on.
So I recommend if anyone's really interested, you go up to the clubhouse and check it out. The mirror does need some cleaning, and that's probably the biggest issue. It's probably removing cleaning. I'm sure someone in the club could help with that, advise with that if that was a real interest for someone.
Thanks. And there'll be more in the future. We could do more than one at a time as well. We'll see how this goes. So we've got more to come. Okay. And lastly, we have the next work party, as I mentioned, on the 31st. And I'd like to thank the lunch crew who shows up faithfully every month to really help. Eileen especially, Sai Valava, Al Takeda, John Reed, and this past month was Barbara Bosworth as well.
By the way, again, I want to thank Maria and Chris as well, the work they've been doing to keep this website up and going. You know, there's always a room for improvement. It's certainly better than what we had before, at least as far as being safe. It's not going to go anywhere. But anytime, if you have any ideas of what we could do to upgrade the website, let us know. But this is new, and I think this is kind of an exciting feature now to actually start to advertise some of these telescopes on our website. So stay tuned on that. Telescope making, I know, Tom, they've already said a bunch of things, but did you have any updates on that at all?
Nothing extraordinarily new. The glass collection we have to go through. We don't have a lot of kits right now, so I'm in the process of looking into purchasing a number of them so that people can come and start working right away. But Mike is pretty happy to start seeing action. And if you're interested in working on a mirror, I say go up to the clubhouse every Saturday afternoon. Either it's like around 11 o'clock in the morning on. Mike is there, and there are other Phil and Ed, I believe, are there also, so to help out with that process. And as people were saying, that we're hoping to put more investment into some automation associated with either the analysis or in terms of grinding mirrors themselves. So we're looking into revamping some of the material, some of the equipment that we do have, or building some new mirror grinding instruments. So, pretty exciting times. If you're interested, head on up to the club.
Thank you, Tom. By the way, this show, there's something for everybody. We have everything from youngsters that are in grade school to old retired people. So you come on out and
even you were up there. You were grinding a little bit.
Well, I haven't shown you how far. We have Mike there helping out Julie Sage, who's 13 years old, and she's making a scope right now at 80.
Yeah, they're pouring a pitch lap right now.
Yeah, and what's his? I forget already. Kevin.
Dave.
I don't know.
It's either Dave or Kevin. We'll get that. I just had a chance to talk to
I was going to say it starts with a K. Yeah, he's in the grinding room. I'm over using an old polishing machine there, to try and not destroy a cave mirror that I'm trying to resurrect. And I know Barry 2 weeks ago was rebuilding the mirror holder in the tunnel to make it easier to use.
Yeah, see, these are activities, going back to, well, we'll talk about them in outreach. These are things that the club had always been really good at. We've been kind of slipping a little bit in the past few years, which is why I thought it'd be a good idea to set up committees specifically for these activities, telescope making. And all of a sudden there's been a surge in interest. So definitely, if you're interested in doing this, check in and we'll get things going for you.
That box behind Mike and Julie, and then behind me in this other picture, that's the testing tunnel. And then in the next room over is the Foucault tester. And they were talking the other day about getting an interferometer set up.
Yeah.
And, you know, to try to make it so it's easier to make this stuff, you know?
Yeah, Mike took, I had donated actually an old interferometer, a beam splitter setup, which would be part of the interferometer, but we didn't have the power supply for the laser, so Mike's trying to locate that now.
By the way, this club has some amazing opticians, optical experts in the club. Mike is one of them. He's done quite a bit. He kind of stays in the background, but he's definitely an asset. All right, now I'm going to let Rich talk about this, but I want to just bring this up again. Outreach is going to have 3 major areas. Now, Virginia, for a number of years, has been doing star parties. That's a tough job to do. And by the way, Mari, she's in your club. Have you heard anything from her at all? Or we haven't.
I haven't run into her there. I don't know why she didn't come here.
Okay, we've been trying to keep in contact. Anyway, I sent out an email finding out who wants to be involved with this outreach club and who would like to set it. And Rich was kind enough to say he'll take over and oversee the whole thing. His job isn't to do a lot of the work, it's to collect all the information and put something out. Give a talk, which we will in a minute here, put something out on the newsletter and the website as well. But we have 3 major areas. One is one we've been doing all along anyway, and that's outreach, star parties, things like that. By the way, notice, whoops, let me go back a minute here. We're selling new company caps now, ATMoB caps. Those are the, I think those are kosher ATMoB hats. So just so you know, we have kosher ATMoB caps now.
They're lined with tinfoil to keep the aliens out.
There's also PopScope. This is right off the PopScope website. It's basically urban stargazing. And Mike O'Shea, is he here tonight? I thought he might be. Again, it's been tough for some people to get here, but he's very excited about working with us on this as well. And that's another area. If any of you live in urban areas, and Bob Toop, I think Bob is going to be working on this as well. Is he here? Yes. Do you want to say a few things about PopScope, or?
Well, I don't know when it was. Last year, maybe even the year before. This sort of started in Toronto and spread around the eastern part of the United States with a major inner city activity for basically showing up on the street without warning anybody and with a portable telescope and engaging people in a friendly sort of a way. So somebody came to the meeting either last year or the year before.
Mike O'Shea.
And I was the only person that responded because it involves a lot of hassle in terms of having to drive to Boston for me and carrying the scope. And it often doesn't work out too well, but he does have a regular gig at the Children's Museum, 4 Point, or Seaport as it's now called, on every Friday, first Friday of the month. So I usually go to that when I'm not going to the clubhouse, and various other ad hoc things. It's most of the people in the PopScope, which is about 15 people, are young, totally inexperienced with astronomy. That scope that you see there in the lower left picture is a Celestron gift, which is very portable. It's almost as portable as my telescope. So anyway, it's something I can see the club not really getting into, except for the fact that it satisfies one of my needs, which is to do outreach with people who don't know anything. But you know, it's not easy. I went up to Lowell 2 weeks ago on a Saturday night and found out that I was in the middle of what they call a winter fest. Incredibly bright lights, a thing displaying 25-foot diameter snowflakes on the wall of City Hall, a merry-go-round.
Yeah.
And the excuse was it was cloudy, but you could just see the moon. In fact, the moon was pretty good because it was almost full and dimmed down, so it was actually reasonable to look at in a telescope. But I was the only person there. So anyway, it's a good connection.
Yeah. I want to mention again, we are the Boston ATMs. It seems like most of us are out in the rural areas. And I think I mentioned the president's message. You look at Carl Sagan, who grew up in the city, and I can't think of Tyson, Neil DeGrasse Tyson. They were city folks, and somehow they got the bug. I think one of them went to a planetarium in the city and got the bug there, but you don't know if there's a Neil deGrasse Tyson or Carl Sagan out there in that group that you might reach when you go to one of these inner city things. And by the way, it doesn't have to be Boston. You mentioned Lowell. I did one for school in the Worcester area, which is actually a lot of minority students there, and the kids love you. They appreciate getting to see things they don't necessarily get to see. So it's definitely something to consider. I'm looking right now and possibly something in the Fitchburg, Leominster area. Again, once I get back in 100% shape, I'd like to start reaching out that way. So it doesn't have to be just Boston, but I think it's a definitely worthwhile thing. And he talked a lot, Mike O'Shea talked a lot about it. Mike is leaving the area, I understand.
I didn't know that.
Yeah, so what I'm going to do is touch base and see if at least we can link with the local PopScope group. You don't have to be the only one that's doing this type of thing. We'll see if we can link with them and at least get them into our loop, so to speak, and work some more of these PopScope parties. At least help them with what they do if we're unable to make the city. Yeah. Okay, and finally, and Dick Coolish brought this up. This is a little different, but the third aspect would be just public lectures, going out to libraries, talking about astronomy. Or you mentioned, what was the meeting again that you were at?
The Model Engineering Society meeting.
Yeah, sometimes these meetings, they might be engineers, whatever, they might actually be interested in telescope making. So if any of you find out there's something like that you're a member of, and you think it might be good to have some representatives from the club show up and set up a booth and a couple of display things. As far as getting club members, I know we was talked to you, we're not getting much of a return from the start parties. These are kids. They're going to move probably to California, all over the country. So with this thing, that way you're planting the seed. You're getting them interested. That site of Saturn might be something that it just connects with them maybe when they're in their young adult life. But we may never see them again. Down here, some people in the inner city, we may attract a few people, some Carl Sagans or Neil deGrasse Tysons. And this is the one actually, public lectures, going to schools, or just going to groups of adults. You might reach some people that could be possible members. So these are the things we want to consider with outreach. We want to plant the seed, the love of astronomy, but we also want to see if we can get some new members to come into the club and join the fold.
I got one other thing to say.
Yes.
About that, the third activity. Some of you may know that back in the December meeting, January meeting, I can't remember, January, somebody had asked Chris for someone to help with teaching an astronomy class, adult education sort of thing, community center in Brockton. And I responded, and I think 4 or 5 other people did. So I wound up being a co-teacher of that class, which started last Monday and runs for 6 weeks. And I'm supposed to be trying to get them to do some observing because that's what they wanted. Not easy because the observing would start at 9 o'clock, which is kind of late for retirees, and one 13-year-old girl was in the class, but still. I think up to 7 or 8 of you have volunteered to be available to open up the clubhouse for that class sometime in the next 6 weeks when we have a good night. So I hope you'll show up for that. Those of you who know, I've already gotten a hold of you.
Yeah, I had worked on that program years ago, and what we did was we taught it in the middle school there in 119, and we actually used it as a track and field area, soccer field right outside there. You can set up there too. There are some problems with lights, but they're not that bad. So that's an option as well. Yes, John.
Dan Winchell and I co-teach a course right now at the Cambridge Center of Adult Ed for adults. And it's an 8-week course. We've been doing this for years, right? Since 2009, I think. And we have an 8-week Tuesday night semester. In between, like now, we have 4-week sort of advanced graduate astronomy, and intro astronomy. So, yeah, we are involved in that.
You know what I would ask? And I'm not trying to dump a whole lot of things on Rich, and Rich will let you get up because he should be the one doing the talking, but one of his jobs is going to be to get the information from the rest of us and just kind of summarize at each meeting what's going on, what have they done, and you guys might want to send just a sentence, just say what's going on, what have you done, Same thing with the Groton group, let them know what's going on with the phases, so we can just publicize. We're doing things and not even mentioning. And I'm just as much at fault. I'll be doing a star party at the Campbell School in Litchfield, I think March 20th. And I've been doing that for years on my own, and yet I am a member of the club, and we should be mentioning, well, this does get done. People are saying we never do star parties. I know I've done a bunch of them without even announcing them. I'm not want to pat myself on the back, but certainly the club should take some credit for these things. So anyway, and this is an important thing. Yes, Dick?
Well, I'll say two things. One is I help with Arlington Astronomy Nights. A fellow named Jeff Alexander has organized them, and we do 3 or 4 nights during the summer, a star party up at Robbins Farm Park. And I help him with that. And it's not really club affiliated, but we're getting good crowds recently. The second thing is that some libraries are branching out from books, and they have what's called a library of things. And the Lexington Library, I believe, has a telescope. Although I will say I had a very, very negative experience with them when I first got it. So, but there may very well be telescopes in libraries around, and that's probably something else we should.
The library telescope program, we had to talk about that a few months ago. All right, very quickly, we'll get on things. I just want to mention, we did get the outreach committee formed. I didn't think we'd get it done in time, but we have. Tom and I are kind of hanging on so we get the transition done. And Tom, if he decides to become, if you want to stay with the group, I'm on Star Party at ATMoB.org as well, but right now, Rich is overseeing the whole thing, and then we have 3 people who are going to take care of the star parties from now on. We have Bernie Kazicki, John Harrington, and Laura Sale is going to be kind of, get them all set. Okay, well, I'll let you take over then.
Glenn is actually going to stay on the outreach committee after he leaves as president, because, he has nothing else to do. Everything you just heard is what we want outreach to be, and more. We can make it whatever we want. What we really need is have people get involved. And back in the 90s, before I went into teaching, I used to organize mostly all the star parties for the club. And we used to do about 25 a year at various schools around the area. And I had just a whole group of people that like to volunteer and come out and do that sort of thing. You don't have to be an expert at astronomy. You maybe know a few facts about your telescope and a few facts about the object you're looking at, and that's all you need. And you just share your love of astronomy with the people that, like you said, oftentimes will never have the opportunity to look through a telescope. And in all the years I did star parties, I never thought even once that we were going to get new members out of it. That wasn't my reason to be. It was because we're planting little seeds. How old were you all when you started astronomy? I was just a kid. And I was lucky enough to have somebody show me some stuff, and here we are today. And there are a lot of people like that. So please consider volunteering. Like you said, Bernie Kazicki, John Harrington, and Laura Sale have agreed to be Star Party coordinators, and you can contact them at starparty@atmob.org. We always need volunteers, and there are already a list of up-and-coming events. We canceled one. What are we on today? Thursday?
The Acton Star Party is postponed before the meeting?
Nope, the Acton Star Party went. The Stowe Center School is postponed to next Wednesday night. There's one in Belmont on the 22nd of March. There's one in Brookline on the 6th of April. And the Groton Community Center, Bob's group, is going to be with us on and off through the 16th of April. Remember, daylight savings time is going to affect this weekend. So spring back or fall forward or whatever we do, I can never announce.
Spring forward.
Oh, something like that, yeah.
Rich, can I just mention the Farrington, I think it's called Farrington, is this Saturday also.
If they can't
That's right.
back, there was a question about whether they wanted to do it or not.
As far as I know, no.
I'll talk to you after the meeting.
No, I think you're thinking of Eileen's thing.
No, there was a Farrington school. I did get an email.
No, I know.
They might want to cancel because of the weather. So I'll talk to Tom. We were kind of working on that.
That's right. You know what that slips your mind, because Eileen and I have clubhouse duty. So I wasn't going to be able to help you out with that. But, things to consider. Glenn, you wrote in the current astronomy magazine about star parties and having a moon in the sky. We're trying to wow these folks. So if you're going to organize a star party, if some school contacts you in your town, or you get in touch with some teacher, try to arrange to have a night when there's some sort of moon in the sky, preferably not a full moon. 4-day-old to 8, 9, 10-day-old moon, that's perfect for star parties. No full moon, right? No, bad. Yes, Ellen?
We had the Acton Star Party on Monday, and I had Beetlejuice. And everyone looked at Beetlejuice. They all went crazy.
Yeah.
One star. That's all
That's
I
all
showed.
it takes.
That's all. And then I showed the Pleiades, and that was it.
So, yes, sir.
Rich,
So it sounds like there are a lot of upcoming activity, star parties. Is it possible, or I don't know, is it currently, is there a spot on the website for non-ATMoB members to get on and see what's coming?
I don't think non-members can see the star parties we're doing.
That's right.
Can
I just speak to that?
By ATMoB announced, but if people are interested that aren't members, they can go on the site.
I want to speak to that because we're invited guests at star parties, especially at schools. Okay? So it's a liability issue. So we don't want to open it up to non-ATMoB members because we can't be held responsible. Essentially, we're invited. So if they want to invite other members of the community to participate, that's okay. But we cannot reach out to anyone else unless they're part of our membership. And it's strictly to protect the kids, largely. So that's the biggest concern. So if you know people that are interested in doing star parties, get them involved in the club. And then, we'll even give them a free membership if they're going to do that.
They can even bid on new telescopes.
Right, yeah, exactly. And if you want to get involved, you don't have a telescope, you can always do binoculars, but we have loaner scopes that you can take to these star parties also. So something else to think about.
Do you want me to talk about the one Monday night, or do you want to talk about it?
Sure, go ahead.
So just as an example of what we do at star parties. So Monday night we had the Acton Star Party. This was the 16th year they put the star party on. Crowds were a little bit smaller than I remember the last time I was there, but there was something about changing the curriculum or something. Amateur telescope makers of Boston volunteers with telescopes are Eileen Myers, Al Takeda, John Mayer, Tom McDonough, Jack Richardson, Hugo and Diego Alvarez, Phil Brownsville, John Reed, Bruce Berger, and myself. Jim Zabrowski, he's the NASA Solar System Ambassador. Is Jim a member of this club or just the Aldrich? I know he's out of the Aldrich.
I think he's a member.
You think he's a member here too?
Member, yeah.
So Jim was there. Gary Green did a slideshow. George Roberts ran the Star Lab Planetarium. Alan McRobert from Sky and Telescope was doing star tours with sky tours with star charts. Bob Finney from the Clay Center lugged his 80 million pound meteorite there again.
He's a member too.
He's a member too. And Mike Francis appeared as Galileo. The kids had a blast. Tom, this is the second year I've been to that event, and Tom's had me be the greeter. And so I was out at the front entrance to the star party, where everybody else from the club was in the back. And so I don't know if you were out there, my line was that everybody that was coming to the star party, this is where they had to pay their admission. And the admission, of course, was just simply to look through the telescope. Early on, we had Venus and Mercury. Very pretty. In the finder scope, you could see both of them in the same field of view, so that was kind of cool. Once those guys set, I popped it up onto the Pleiades, and that's what we looked at. Out back, you guys were looking at all kinds of different things back there, so it was kind of fun. They gave us chili. There was yummy food afterwards.
4 different kinds.
There were a bunch of different kinds of chili. It was nice. Sometimes we get pizza.
Well, they gave us kerchiefs.
Yeah, the little bandana thing. I didn't bring mine tonight.
Yeah.
It was nice. It was very nice. So, and it's fun. You get to hang out with people from the club. You get to meet new people out there in the world. You sprinkle a little astronomy on kids, and kids of all ages, because the parents like it just as much as the kids do. A lot of them have never seen stuff through a telescope, so you're really impressing them. We had Venus and Mercury, but no other planets, no moon to look at. But there was no want for objects. They loved it. It was fabulous. So that's why I do it. I feel good when I walk away from a star party. I feel like I contributed something to the world. Mm-hmm. And so that's why I do them. And I would encourage everybody to try it. If you've never done one before, come on out and try one. Like I said, you don't have to be an expert. You don't have to be an expert at all. They're fun. They're a blast. And 65% of the time you get clouded out anyway.
Only 65.
It feels like more sometimes. But you'll be hearing more from me as the months go by. So, bear with me. Just get the hook when it's time for me to get off the stage, because I can talk for a long time. So thanks. All right, so there you go.
I've been there when you get 100 or 200 kids all excited about what's going on outside, and you go out and it's clouded over. But we've looked at the etching on the glass on the street light a quarter of a mile away. The kids get a kick out of that. And with one high school group, I showed them the special at the local pizza shop a quarter of a mile away. They had to turn upside down to read what it was, but they got a kick out of that. Rich mentioned the moon. I'm going to be doing a star party again around the 20th at the Campbell School up in Litchfield. And one of the things I do with that is high school kids with these. And I bring in a 10-inch Dob myself for the main stuff, but also I'm going to bring a little 4.5-inch Orion Dob that's very user-friendly. What I'll do is I'll set that up first, and I'll set it up on the moon and quickly show them how to position the cell phone and get a picture of the moon. It takes a little bit of practice if you've ever tried it before, but then I leave them with that scope. They can aim it, and the moon's very easy to work with, so it's something for some of them to do while they're waiting to look through the scope. So, as Rich mentioned, star parties, are a lot of fun. At the high school, sometimes it is a star party. I had a student one time, there used to be a badge of honor to let out the loudest, grossest fart you could in the class. And one kid, it was a standard group, let one go, and he's chuckling himself, and I looked at him and said, "That's the smartest thing you've said today." And he never did it again. Okay, couple things coming up. As was mentioned earlier, there are 3 office positions that will be open, so we're going to need a nominating committee to select the group. It'll be, during the next month, we'll be setting this up.
Glenn, we always need a nominating committee.
We always need,
No
yes.
matter what.
And it's got to be 6. It can't be 3 like I thought last time, and I had to Shanghai people. So I'd ask you now, we want to get this meeting going, we're running kind of late, but if you'd like to be on that nominating committee, let me know. I will be putting out an email tomorrow, or announcement within the next few days, that we need 6 people to, we'll vote on that next time. And also, I'd like people who may be interested in these positions to come forward. It'll make the nominating committee's job a little bit easier if you have some people already set to go. Messier Marathon will be coming up on the 17th, and Richie, we're going to talk about that, so I'll give you the floor again.
All right, just for a minute, because we're running late, it's getting late.
Yeah.
Every year, right around the end of March, if you're really good and it's clear and you've taken your NoDoz and you've overdosed on caffeine, you can see all 110 Messier objects in the same night. I've never done it. I'm not much of a marathon guy. I usually fade at about midnight, just before I get to the Virgo cluster. I'm like, you know what, that's enough. But it can be done. So this is the time of year we do it. I expect to be up at the Clubhouse that weekend, and we'll make sure the pads are shoveled off. If you've never tried it, even if you just come out and look at 10 of them. Just look at 10 of them. Somebody just sent me an email with the monthly messages.
Yes, yeah.
And so even if you look for just 10 of them, that's awesome, you know? And we'll have fine charts, and you know, it's fun. Just come out and try it. Dress warmly. It's cold in March.
Okay, and I'll be doing that double star marathon.
Oh, yeah,
I came up with a list of 110. Astronomy Day on the 21st. We'll talk more about this next month, but I did want to remind you, I did talk to Haystack, and we've got a conference from Reserve for up to 100 people. I don't know if we'll get that many, but I just contacted Nancy Coterie there, and I suggested, why don't you invite your community first, the people that work at Haystack and their families. We'll give them the first slots. I'd be very surprised if they filled 100. But once that's done, then we're going to reach it out to some of the local communities, Westford, Groton, Littleton, towns that are within the Haystack area. So we hope to have enough. And basically, I'll be giving a talk on getting started in backyard astronomy, and I'll be looking for a couple of ATMoB volunteers to help work with you that night, maybe bring telescopes.
Well, that's the weekend of MEEF, just to let you know.
All right, well, there'll still be 3 or 4 of us that'll be around there. We'll get something going. Yeah. Anybody have any updates on the old business? New business. Okay, we're going to turn things over now to Andrew Chael, and I haven't had the pleasure of meeting Andrew. Is he? And now we'll get him set up. I didn't get to meet you earlier. I'll read a bio while you're getting set up here. Andrew Chael is our guest speaker tonight. And this is kind of an interesting project. You may have been hearing about this. I even talked to a couple of my fellow retiree teachers about what's going on tonight. They're not even astronomers, and one heard, I heard they're trying to take a picture of a black hole. So apparently even non-astronomers have heard of this project. Anyway, Andrew Chael is a graduate student in the Harvard Physics Department. Originally from Albuquerque, New Mexico, he became fascinated with astronomy and astrophysics from stargazing on camping trips in the desert and field trips with a very large array. Andrew earned a BA in physics from Carleton College, where he did work in observational pulsar astronomy. At Harvard, he works with Shep Dolman and Ramesh Narayan on both theoretical modeling and data analysis for Event Horizon Telescope observations of Sagittarius A, the black hole in the galactic center. So as soon as Al and everything set up, we'll have Andrew take over. Are you good to go?
Yep.
Katie Bauman. There are a number of people in the area that are working on this project. Yeah, Katie Bauman. Right.
You can give a shot here first.
Okay, Andrew, the floor is yours.
Thank you so much for inviting me to this. This is my 5th year of graduate school and the first time I've given a public talk like this, so thank you so much. This is, like I said, work I've done with a lot of people, and sort of most of it is not mine. It's actually work that we've done all together. A lot of it from Katie Bauman, and I would recommend, really, she has a TEDx talk that's on YouTube that's really great if you want it. A lot of it I'm going to be covering, but if you want a refresher later on, you know, look at that, and she gives an excellent talk. So many of the images that we've seen today, and which you may be familiar with astronomy, are incredibly, crisp and precise, and we have access to HST images. Soon we'll have JWST images, these beautiful precision images, but in this field, we're really pushing it in terms of very blurry images of the black hole, but I hope I can convince you that that itself will be impressive once we eventually figure it out and get it working. This is a simulation from the movie Interstellar, which is sort of the same thing I do in terms of simulating black holes, but with the Hollywood budget, so it's a little better. Okay, so what is a black hole? You may think that black holes are incredibly complicated. You've heard about things like trapping of light and wormholes, but really a black hole conceptually is very simple, and one of the simplest things that can be studied in physics. And the way to think about it that makes most sense to me is that a black hole is just an object that is simultaneously incredibly big and incredibly small. So it's incredibly big in that it's incredibly massive. Smallest ones have masses of greater than the sun, up to billions of solar masses, but incredibly small in that the radius, the characteristic radius, the Schwarzschild radius, is generally, for the biggest black holes, only about an AU, and for solar mass black holes, much smaller. And so these were actually, so it's a 20th century discovery. The idea of a black hole actually goes back, or something like a black hole, actually goes back much longer. So this is a paper from 1784 that first came up with this idea of what this guy, John Mitchell, called dark stars, which is, he just said, okay, what if we take the escape velocity, which is this expression here, it's the velocity you would need launching straight up from a planet to escape the gravitational field entirely. What if you take that velocity and set it equal to the speed of light? Because we know that nothing can go out faster than the speed of light. What would this tell us about the object? And basically, you just solve this equation. It tells you that if you get a radius of this size, your escape velocity will be the speed of light, and you won't be able to escape the object. This is sort of a curiosity from the perspective of Newtonian physics. I mean, I think back then people didn't even think that light was affected by gravity. But this sort of gives you this interesting characteristic size, which, like I said, for the Earth would only be 9 millimeters, so you have to squeeze the entire mass of the Earth into a marble about 9 millimeters big. For the Sun, a couple miles. I think this is an early example also of something we see a lot of the time in physics, which is a characteristic scale at which the problem breaks down. And so you might know, like, if you're looking at Newtonian physics, it doesn't make any sense. What's going on here? This is, it took them a couple hundred years, or roughly 100 years, to figure out what exactly was going on, but this was an early sign that at this scale, with this much mass in this small of a space, something isn't right with the physics that we thought we knew. So fast forward a little more than 100 years to 1915, Albert Einstein came up with his theory of general relativity. But actually, the idea of black holes didn't emerge for almost 50 years after his original theory. But something that was there from the very beginning was this idea that now, with general relativity, gravity affects light. So this most famous first experiment done to test general relativity was the 1919 solar eclipse. Eddington and a bunch of other people went and looked and did observations of the eclipse where they could see the stars right next to the sun because the eclipse was blocking the light from the sun directly, and they could see that the stars right behind the sun, their positions was being distorted. by the fact that light was traveling through them, was traveling through the gravitational field of the star and bending slightly as it grazed the surface of the star, of the sun, and came to Earth. This was his first major success of general relativity. And right from the beginning, we knew that light was being affected by gravity. The next year, in 1916, Schwarzschild came up with the first full solution in general relativity, which is his famous Schwarzschild metric. This basically looks a little complicated, but it spits out in the end this same radius that we got before from that simple test of setting the escape velocity equal to the speed of light. So, and then in the Schwarzschild case, it tells us that inside this radius, nothing can escape. Everything is compelled to go toward the central object. When Schwarzschild came up with this, people didn't really think this was a physical thing. They thought that this solution described space-time outside of a planet, for example, but inside the planet, something, the mass distribution was changing. So this idea of there being a Schwarzschild metric, a Schwarzschild radius inside which everything collapses to a singularity wasn't really important in the real world. And then unfortunately Schwarzschild died like 2 years later, so he couldn't convince anyone, even if he believed it himself. Died in World War I. The same year, David Hilbert was actually the first person to give a calculation of how a black hole might appear. So even though the large part of the scientific community really, I think, didn't take this idea seriously that black holes could exist physically, people in mathematics and physics were playing around with it, playing around with the extremes of these equations and seeing what would come out. And so he showed that a black hole would cast a shadow on the background light, that's the effect we're hoping to observe with the Observatory Horizon Telescope. In 1930, Chandrasekhar discovered that white dwarfs have a maximum mass, after which they will inevitably collapse. This gave a little more credence to the idea that maybe what's going to happen after the white dwarf collapse may be a black hole at the end state. But then really we had to wait until the 60s with the second golden age of general relativity and the discovery of quasars and X-ray binaries and astrophysical black holes to really come to the realization that black holes don't just exist, that they're incredibly common in the universe, and that they're incredibly important to understand not only things on the small scales, but just the evolution of the universe in general. In 1963, Kerr discovered the general solution for a black hole. So 50 years almost later, after Schwarzschild, he discovered what sort of a physical black hole that is actually rotating will behave like. And basically the same year was the discovery of quasars. And so quasars were discovered in the radio. We saw these point-like sources of radio emission. And when we looked or they looked to see what the corresponding optical counterpart was, they just saw basically what looked like an ordinary star. This was sort of a puzzle because most stars don't emit radio. And it took people doing precise spectroscopy of these stars to realize that these were actually incredibly far away. So they weren't stars, these were a million to a billion light years away, and that they actually were in distant galaxies, not in our own galaxy. So if you use a modern telescope, like this Hubble image, and subtract out the light from the central object, you see that there actually is a galaxy behind it. This one central point is outshining the light of all the stars in that galaxy. And it's doing that within the radius of about the Earth's orbit. So the reason this is possible is, again, because black holes are incredibly small. And so this process called accretion allows black holes to liberate an incredible amount of gravitational energy. When something falls to the ground in the Earth's gravitational field, it's liberating its energy by its gravitational energy and converting it to velocity. Similarly, if something falls in from very far away into a black hole, it liberates its energy and generally produces light. The difference is that it can, because black holes are so small physically, it can fall in an incredible distance. And actually this accretion power per unit mass, the amount of energy per unit mass that can be liberated, is about half of the rest mass energy, the mc squared of the object. For comparison, for nuclear fusion, it's almost 100 times less. So this process, which we think of as one of the most energetic processes in nature, is actually 100 times less energetic than just something falling in onto a black hole, releasing its energy in light. Recently, we've entered what many people think will be a third golden age of relativity in the discovery of gravitational waves with the LIGO experiment 2 years ago, and they just won the Nobel Prize this year. So this is really opening up an entirely new way of looking at black holes. It's a different regime than the one we're studying. We're looking at supermassive black holes, which are 10 to the 6, a million to a billion solar masses. LIGO is looking at things more like 10 to 100 maybe solar masses. But it's giving us an entirely new way of looking at the universe that isn't light. For the first time, we have a way of looking at something from across the universe, not in light. But LIGO doesn't tell us how black holes would look. So that's the goal of our experiment. What does the image of a black hole look like? You can imagine being a distant observer, and you're seeing rays come from the black hole. Actually, in this picture, I think rays are coming from you, but this thing's going backwards. Because the black hole, like the sun, is bending light, some light rays will be bent, and so if you're tracing back the light ray that hits your eye, it might not come from directly straight across. It might come from behind the black hole. But a black hole, because light rays can get so much closer to the surface, again, because it's so small than the sun, light rays can be bent in much greater degrees, and they can actually just fall into the black hole. Inside the Schwarzschild radius, any light rays that trajectory would pass that radius actually end up inside the black hole, and we don't see them. So we can hope to try to invert this picture and get an idea of what the black hole will look like. We have this bright, energetic accretion disk around it that's providing a source of light all around the black hole. And the black hole, even though it's black, is going to imprint itself on top of the emission from that disk. So the first time this was done fully was in 1973 by Bardeen, and he sort of calculated this abstract shape, which is what a black hole will look like generally. But it wasn't until a couple of years later that we sort of got, he also said, he viewed this as a very mathematical exercise, right, and said that it's conceptually interesting, but not astrophysically very important to calculate this shape. It's a toy problem that you can do for fun, but now here we are, 4 years later, trying to actually observe this. So I think this just shows how things that you think are impossible eventually can, hopefully, come to fruition. But sort of the first picture, the first thing that has a realistic accretion disk on top of it, came a few years later by Luminet in 1979. I actually really like the story of this image. It's sort of very artistic looking, and this actually came because he was getting his calculations out in a big roll of paper from his 1979 computer, and then he was going in onto a piece of graphite paper and coloring in each dot based on the intensity that the computer gave him. So he gets this very nice drawing almost of a black hole. And here you see the accretion disk, which in front you can sort of see it looks like a disk, but behind the black hole we see the accretion disk go over it, and that's because we're seeing rays from the disk behind it that are being bent over the black hole and coming to us on a curved trajectory. And then inside the black hole we can't see anything because rays that cross that event horizon get swallowed up by the black hole and we don't see them.
This is drawing from a printout.
Yeah, it's the drawing from a printout, exactly. And yeah, so something I do in my research all the time is make similar images, but now we can do them like this on a computer directly. It's easier. And you take a model and you evolve the rays of light forward through that model, and you see what it looks like to a camera at a far distance. And so, for example, here we have this one that was in 2011, which shows the same shadow, which is a characteristic size of 5 Schwarzschild radii. So because black holes are incredibly small, you might think that they're not going to be very important to galaxies, to the universe broadly outside of their small 1 AU region. But actually, there's been a lot of recent work to show that black holes are incredibly important in regulating the structure of galaxies, the formation of galaxies, the evolution of galaxies across the entire universe. So for example, if we look at this, this image of Sagittarius A, in the optical, we see a nice galaxy with very prominent dust lanes. But if we look in the radio, we see that actually this galaxy is emitting these huge jets, which extend much further than the radius of the galaxy itself. The galaxy is a few thousand light years across. These jets actually go out to almost a million light years. And sort of the latest images of this, I really like this image because it shows the actual size superimposed next to an image of the sun. So these jets go many, many degrees across the sky. You could see them yourself. Obviously, they're incredibly faint in radio. So these jets are taking energy from the center, from this black hole that's only about as big as the orbit of the Earth, and they're depositing it on huge scales. So they're pushing gas out to huge distances past the galaxy itself. And this has huge effects on neighboring galaxies, on the evolution of galaxies, on whether or not matter can fall in and form galaxies in the first place. So this is a really active area of research, determining how this energy is transported outward, how it's affecting the structure and evolution of galaxies throughout the early phase of the universe in particular, and even up to now. And you can use radio observations to show that these huge structures that are a million light years across actually extend all the way down to just a light year. So you can look at different wavelengths. As you get to shorter and shorter wavelengths, you look closer and closer in toward the central black hole, and you see that this jet actually goes all the way, and is carrying material and energy all the way from that very central point outward to these huge scales. But we don't actually have to go to another galaxy to see a supermassive black hole, because we have one in our own galaxy that is much dimmer, but is still extremely interesting. And this is what we're actually hoping to observe with the Event Horizon Telescope. It's named Sagittarius A star because when it was discovered in Sagittarius, they thought it was exciting, so they added an A star, onto it. So one of these naming conventions is not the most formal. So yeah, if we look into the Milky Way and we go on a journey from our position in the Earth through toward the center of the galaxy, looking at different wavelengths, getting closer and closer to the center, we see in this inner volume these stars, which are moving really rapidly over the period of like 15 years. And so people have been tracking these stars and their orbits since about 2000 now, and they're looking in the near infrared using adaptive optics, and they can see that all these stars are orbiting a central mass that we can't see. They can trace this orbit out in 3 dimensions and look and determine what the mass of the central object is. And what they find is that the mass of the central object is about 4 million solar masses, which is completely invisible to us, other than showing up very slightly in radio. And so this is the strongest evidence, I think, before LIGO, before the merger of 2 black holes that we got a few years ago. It's the strongest evidence that black holes actually existed and that they were really black and weren't emitting any radiation. Zooming out, or zooming in rather, we see that these stars are coming in with a few tens of AU close to the black hole. Actually, this S21 is about to complete its first orbit that's been observed, so it's going to pass right next to the black hole this summer, I think, and they'll be observing it with this new instrument called gravity, which will, I think, be, yeah.
Just a question, you said how many AU is that?
These are roughly 15 AU, I think. One of them.
Do you know, is that a sub-arc second we're looking at?
So this is 0.1 arc second.
0.1, okay,
Yeah.
thanks.
Yeah. But anyway, so one of these stars has completed a full orbit. It's going to be making its pericenter approach to the black hole this summer, and they're going to be observing it to see if they can see the relativistic effects of the black hole. This is, the orbit of Mercury in the solar system is precessing very slowly due to the general relativistic effects of the sun. This star's orbit should do the same thing, but much more dramatically as it approaches the black hole. Zooming in closer into the central point, we see a radio source, but for a long time we've just been able to see a blob, basically emitting in radio. Hard to say much about it other than we know there must be a black hole in here because we know there's 4 million solar masses in there, and it's shining only very dimly. So just advertising other work that I'm doing. So I do sort of work both in computational modeling of black holes and in this more observational image reconstruction domain. And so for a long time, since we aren't able to observe, all we've had to go on the structure of black holes, on the structure of Sagittarius A star, is this is theoretical computational models. So this is an example of a simulation that was done by one of my collaborators that shows what this accretion disk around the black hole will look like. And one of the interesting things about the center of our galaxy's black hole compared to many in the distant universe is that it's actually got a very thick accretion disk. And this explains why it's so dim compared to these ones we see at millions and millions of light years away. They actually sort of razor thin disks which are emitting tons of energy and radiation, whereas we have this big puffy object. So for a long time, we've only been able to, with these studies, with these simulations, compare what we get from the simulation to sort of a total spectrum of Sagittarius A star. Because we can't resolve it, all we've been able to do is look at what is it behaving like over different wave bands, calibrate our models, get some idea of physically what's going on that way. But now, with the Event Horizon Telescope, we're finally hoping to be able to compare these simulations directly, not only to spectra across different frequencies, but also to images directly resolving the structure of the black hole itself. This is a movie I made, which is not as nice as the Hollywood one, but still pretty good.
Can you explain how to interpret this?
Yeah. So this is just a lot of information going on, but it mostly is, this is the density of the gas. So like I said before, it's a really thick puffed up disk as compared to these razor thin disks that we see, we expect to see in other galaxies. And this on the left side is basically the magnetic field. So the magnetic field in these systems is incredibly turbulent, and this drives a lot of the emission that we see. So we actually see the emission tracing the magnetic field in this image, in this movie. If we go back to the movie. So the movie shows this sort of same turbulence that's imprinted on it by the magnetic field, but within the central black hole being evident by the fact that we're...
And how are you determining the magnetic field, something so small and far away?
So the magnetic field strength is determined by how bright it is in synchrotron. So the emission from the object is synchrotron emission, which depends on the magnetic field strength of the black hole. I mean, it's still pretty open question exactly what the magnetic field
I'm
strength.
not familiar with that term. What would you call it?
So basically electrons that are spiraling around magnetic field lines, and that's how they emit radiation. And so that depends on how strong the magnetic field is. If it's stronger, the radiation will be brighter. So that's how we get some idea of the magnetic field strength. But actually, it's still a pretty open question because it also depends on how hot the electrons are and the density of the electrons. So all three contribute to the power that we see. So the exact proportion is still up for grabs. So in these simulations, we start with some initial conditions and just see what happens, basically. So going back to this picture, the goal of the Event Horizon Telescope is to take this next step and look into the center of this image and resolve an image of the black hole, resolve this shadow, test general relativity at these extreme environments, and also learn a little bit about what's going on in this plasma around the black hole. What are the processes that are liberating all this energy as matter falls that last few Schwarzschild radii into the black hole. So how do we do this? We look at the black hole, we see that it's got it's got sort of persistent evolution, but this black hole shadow is the thing that we're really trying to observe. We really want to design a telescope that is sensitive enough to be able to see this shadow so we can test general relativity, show that it folds all the way down to the very outer edge of the black hole, and also see if there's any new physics emerging beyond general relativity as well. But this black hole shadow is so small because the black hole is so far away and itself is only about less than an AU big. Its angular size is about that of an orange on the moon. It's 50 micro arc seconds. But even with the best telescopes on Earth, we can't see an orange on the moon. So here, for example, in this image, each pixel of this very nice image has about 1 million oranges in it. So we can't hope to do this with a single telescope. You probably all know the diffraction limit tells us that the angular resolution of the telescope is proportional to its wavelength and inversely proportional to the size of the aperture. And the wavelength that we use is pretty fixed by two things. It's fixed by the fact that in radio, the Earth's atmosphere is only transparent at certain wavelengths. It's also fixed by the fact that there is a bunch of stuff between us and the galactic center that scatters emission at many wavelengths. We have to go to incredibly short wavelengths to get past this scattering and actually see all the way to the galactic center. And so what we settled on is basically 1 millimeter in wavelength. Once we have 1 millimeter in the numerator here, looking at 50 micro arc seconds and solving for the telescope size tells us that we basically need a telescope that's the size of the Earth. And I don't think anyone's going to fund this, building this lovely conceptual illustration that was put together. And even with this Earth-sized telescope, we are not going to be able to see all these spine scale features we see from the movies, all this turbulent stuff that's happening from those magnetic field lines that are twisting up and rotating around the black hole. Even with our Earth-sized telescope, we just get this blurry image, which will be which is good enough to determine the size of the shadow, but all this fine scale physics is still inaccessible until somebody allows us to build a telescope that's even bigger than the Earth. So basically, the takeaway here is that we are incredibly lucky that our black hole is not a little bit further away, or not a little bit less massive, because even then we would have no hope of actually seeing this shadow feature.
Yeah. So when Hollywood makes these video simulations of black holes, like the ones in Interstellar, how accurate are they, do you think?
So the simulation in Interstellar was incredibly accurate, except for the physics that it intentionally excluded in order to make it prettier for a movie. So I don't think it'll do that. So one thing that you see in these simulations is that it's brighter on one side, and that's because the disk that is moving towards you is being Doppler boosted. So its emission is being beamed into your line of sight, whereas the stuff that's going away from you, you can't see as well. In Interstellar, they made a nice big circle so that it looked, very bowl-like and like a nice circle. But I think basically they just ran real code to generate those images just with an incredible budget. So pretty accurate. So if you think about how a telescope works, it's taking, an Earth-sized telescope will be taking light from the black hole and coherently adding it as it reflects in the dish and is combined at the focus. So since we can't build a real telescope the size of the Earth, we can still do something approximately like this by using telescopes all over the Earth, taking the light from the black hole and combining it in a computer. We record the light as it lands on the Earth on all these different sites, and we take all of our data to a central computer and do our magic and try to figure out how we can reconstruct an image. So the Event Horizon Telescope is basically just that. So we have 7 sites all across the Earth where we go out every year and we record data, and we then take all these data, which takes up many terabytes, and crunch it all together, and at the end of the day, come up with just a few numbers which tell us something about the black hole, and hopefully this year, just a few numbers that tell us enough to reconstruct an image of a black hole for the first time. So we have sites, mostly in the Western Hemisphere, from ALMA in Chile, the South Pole Telescope, to the submillimeter array in Hawaii, in Arizona, Spain, Mexico. We're using a technique called very long baseline interferometry. So the idea of very long baseline interferometry comes from the fact that any image can be represented in 2 ways, both as the image itself and as its Fourier transform. If you're unfamiliar with the idea of a Fourier transform, basically one way to think of it is just that it's another way of, you don't know more about it than it's just another way of representing the same data that is in an image. So for example, in a wave, in a time series here, we can represent this wave, this as a complicated curve here, or we can break it up into individual waves and represent it just as a sum of these few individual waves, or a sum of certain frequencies. The same thing is true for images. And in a telescope, the most obvious place this pops up is that your point spread function is the Fourier transform of your aperture size. So all these rings and side lobes you get around a point source in a telescope comes from just the Fourier transform of this, your aperture. So here's the James Webb Space Telescope. So if we had a telescope that was the size of the Earth, we'd be able to measure all of these different frequencies. Basically, each frequency corresponds to sort of the separation between 2 telescopes in our array. So it's telling us something about the size of different features in the image. And so this process is invertible. We can just go back and forth. If we had a full telescope, and we could collect all of these, all this information, we could go directly to this information of the black hole. So if we had this full Earth full of telescopes, all talking to each other at the same time, we could fill in this whole space in this frequency domain and collect all of our data together and make one image. But we don't have that. We only have a few telescopes scattered around the Earth. And so what this gives us effectively is just a few points in this domain. And so everything is very sparsely sampled, and we can't add things up directly and just transform back to the image. We have to be a little more clever than that. So each separation between the 2 telescopes is telling us just something about one frequency in the image, one wave in this decomposition of the image into individual waves. And since we don't know all of them, we can't combine them all and just get the image back. We're helped out a little bit by the fact that the Earth is rotating. And so since the Earth is rotating, the distances between these telescopes is actually changing when you view them as projected onto the sky. And so we're not actually just seeing a few points in this plane of frequencies. We're actually seeing different tracks that are carved out as the Earth rotates and as these distances, as seen from the black hole between the telescopes, change. So we have a little bit more data to work with than just if the Earth wasn't rotating, but still, to reproduce an image is not a direct one-to-one process. So this is just an example of how this rotation helps us in reconstructing an image. So basically, this is the image, the simulated image, and this is showing reconstructions that are happening with data that is cumulatively being added as the Earth rotates. So if we start out with only a little bit of data from just these few baselines, we get a pretty bad image. But as we accumulate more and more data over the course of a night, the simulated image sharpens up by quite a bit.
It really looks close to the simulated image.
Yeah. This is a best case scenario, but yes.
Are those actual measurements on the right side?
So these are where the actual measurements have taken place and will take place, yes.
that image developing on the right.
This is a simulated image. So we're taking a plan of our telescope and we're looking at this fake image and we're simulating it.
A question?
Yeah.
Is that actual data or simulation?
It's simulation. We are still working on the actual data. We're hoping to get it out sometime this year.
And I think you said this, but this data has to be simultaneous for multiple telescopes.
Yes, exactly. Yeah, so basically the idea is that you add up data coherently from all the telescopes. So you record basically just all the light you get as a certain telescope. It sticks out many terabytes, and then you combine it all to get information on each baseline.
Andrew, with the Earth going back and forth different sides of the sun, would that increase the baseline?
You would have to do it simultaneously.
Oh.
So you'd have to, if you had telescopes scattered around the Earth's orbit, that would increase the baseline, yeah. And actually there is a Russian satellite called Radio Astron that does a similar technique at longer wavelengths, but on a space baseline, so it goes out pretty far. Unfortunately, because that's only one baseline that's really long, that's telling you things that are about very fine structure in the image. And since we only have one of those, it's not easy to use that to get information about all the fine scale stuff you really want to get. So what has the EHT accomplished so far? Basically, with our few baselines, a few measurements that we've been able to make in the past, we are able to get sort of the general size of this black hole. And so this plot here is telling you, if you look at the length of the baselines in wavelength, the separation of your telescopes, and you look at how much power you see in between each of these pairs of telescopes, you see this fall off. And you can fit models to it, which give you a characteristic size here. So this is a frequency that corresponds to a size of the black hole. And sort of the characteristic size you get here is only about 4 short-tailed radii. So this is really saying that even in the very innermost regions next to the black hole, everything is coming from only a few short-tailed radii, less than a few tenths of an AU close to the black hole. So you can see here that there are 2 models that sort of explain the data equally well. And this is basically the difficult problem of image reconstruction, is that with only a few data points, you can fit this, for example, with just a blob, a Gaussian, or with a ring-like model that actually has the sort of structure of the black hole shadow that we see. And both of them fit the data well in this case. Going to more recent observations in 2013, we were able to show that this Gaussian model is slightly disfavored compared to this ring model, which fits this uptick of the data at the end. So we're starting to get an idea that the structure isn't featureless. It's not just this blob at the center of the galaxy, but there might be something more interesting going on. So in 2017, we took observations for the first time at all 7 of the EHT sites. And here are some pictures from all of that. Unfortunately, I was here in Cambridge coordinating things, but this year I'm hoping to go to the sub-millimeter array in Hawaii. And at the end of the day, they give us all these disks, hard disks, each many terabytes of data, and they're correlated together, and the number crunching is going on now to produce one of these images.
Is that going on right at Haystack?
Yeah, actually the correlation itself goes on at Haystack. So you need a supercomputer to do the correlation, and then there's an extra step after that to take the data and then produce the image. So that's going on here at CFA and also elsewhere in the world. But the correlation is done at Haystack because they've been doing that for decades with other experiments. And so for the first time, we're hoping in 2017 to get a image of roughly this quality that shows this shadow feature and tests general relativity in this extreme environment close to the black hole. Yeah, so I think I will stop there. I can get more into technical questions about how imaging is done. Yeah.
Just a question. I know that at Haystack, years ago, they built, I believe it was a sub-millimeter array of radio telescopes going out to Hawaii.
Yeah.
Is that the station that's currently being used?
So that's this one here.
Okay, yeah, so we actually saw them right across the street from our clubhouse.
Yeah.
Right on Sunday.
Yeah, so sub-millimeter interferometry has really taken off just in the last 15, 20 years. I think the sub-millimeter array is one of the first ones. It was built at Haystack, and then now it's on Mauna Kea. And now with ALMA, which is somewhere, ALMA is here. There's only one dish. ALMA is about 40 dishes. I think some of them has about 10-ish. ALMA has roughly 40 in Chile, but based on the same principle and the same sort of design as the SMA. Yeah. And all of them are being combined together into the EHT. Each of them is independently its own operating observatory that can by itself look at structures that are much bigger than the black hole. We have to observe by combining them all together in the
Are
EHT.
these telescopes dedicated to EHT or are they used for other things?
No, yeah, so that's one of the big challenges of the EHT is that each of these actually always are used 90% of the time, 99% of the time for other science. And so in an individual array, the EHT is just taking the principles of something like the submillimeter array, combining different telescopes, and scaling it up to something the size of the Earth. Well, the submillimeter array has an advantage in that it's designed to work together all the time. So each telescope can be designed to work well with each other telescope, and it's all engineered to behave in a certain way. Whereas we're trying to take telescopes that are each engineered to do different things and combine them together to work together in a precision way to produce one image. And so that actually introduces a lot of additional error and uncertainty. Is that how we have to understand how each telescope behaves independently before we put it all together.
How do you coordinate the timekeeping that you must have?
Yeah. So so one of the things that allowed the EHT to exist is that we got funding to give each of these sites a hydrogen maser. So the hydrogen maser is a precise atomic time standard, which they can use for other things as well, but we've given them, or my boss has given us them to record the times for EHT observations. So they can use that to record things, very quickly. Yeah.
Is anybody thinking about a telescope with a diameter from the Earth to the Moon?
Yes. So that's sort of in our future horizons, dream big plans. Actually, we had an undergrad this summer whose full-time project was looking at putting various satellites between the Earth and the Moon. I think going the next step and having a dedicated array of telescopes on the Moon would be incredible, but seems a little bit far off. But yeah, the idea at least of putting several into space is possibly something that we might see over the next decade. But the Moon would be better.
Are any observations being done for Haystack itself?
So there have been many test observations that were done at Haystack itself. I don't have a slide with that, I should have, where they would test the equipment that they then send off to these other sites. But Haystack, well, there are two things. Haystack is sort of hard to schedule, I think, on its own, but then also our primary target, Sagittarius A star, is pretty southern, so it's hard to see from here.
Another question. Sagittarius A star is spinning. Is that right? Or do we know that?
We don't know that, so that's one thing we hope to know, or to learn a little bit about through the EHT.
So, all right. So then we don't know if it what that orientation of that axis of spin is.
No, yeah.
Spin is.
Yeah, you might think that everything is lined up, so maybe the spin axis is oriented with the axis of the galaxy's rotation, but that's really not known actually. So this is one thing that you can, the shape of this shadow feature is actually dependent on the spin. And so it turns out that if the black hole is spinning, this side of the shadow is scrunched, it's spinning towards you. So the material is rotating around this way. This side of the shadow becomes sort of elongated and flat. So you can hope to use this picture to then determine what the spin is. But it's still an open question. Okay.
Just curious about what the accuracy of the hydrogen maser atomic clock has to be to crunch all this data simultaneously.
Yeah, so I'm not an engineer, so I'm not the right person to ask about that. I don't want to give you a number that's inaccurate.
I remember about maybe 30 years ago at
Yeah.
Haystack, they showed us the same thing when they were just doing the
Yeah.
galaxy itself, and they were using tape. And they made
Yes.
tape at the time and pulling it all together.
Yeah.
And I think it took months to log it all.
Yeah. Yeah, actually, when Shep, my advisor, gives this talk. He has a slide that still shows the sites of different places having tapes and little wheels moving around. And every time he comments on how this is outdated, but I think he keeps it in. Yeah.
Would it be feasible to look at other targets once you've actually seen such a star?
Yes, so we are looking currently at many different quasars and active galactic nuclei. But we also have another main target, which compilation of many slides. Yeah, so our other main target is M87, so giant, massive elliptical galaxy, which I don't have an optical picture of, but the famous Messier object, really big blob, elliptical galaxy, which has this huge jet coming out of it. That actually was one of the first astrophysical jets to ever be discovered in the optical about 100 years ago. And you can see it really prominently in radio. And this is an image of what this jet looks like at the best resolution we have currently, which is done by the Very Long Baseline Array, which is an array, a VLBI array that was built in the late 80s and early 90s. And so what the EHT hopes to do is look at the central black hole of this evolving jet, which is sort of in this region here. And because this galaxy is, 10 times further away from us than our galaxy, than the black hole in the center of our galaxy, it fortunately also happens to be about 10 times more massive. This is one of the most massive black holes that's known. It's about 1 billion solar masses instead of just 1 million, instead of just 10 million roughly. So it will, So we're hoping to also see see what this black hole looks like, and hopefully also resolve its shadow.
Do you have any tips or resources on sharing some of these discoveries with the general public? It's a really complex topic, but are there any resources or?
I would like to learn from you, but what the best way is to share these to the general public. We have a new website, which was made by a fantastic undergrad that we had over the summer who's specializing in science communication, which was great because our original website was made in like 2005 and not updated since then.
And what's the website?
The website is eventhorizontelescope.org. It's the first thing.
I think I was able to just Google Event Horizon Telescope and get to it.
Yeah, and so, but yeah.
How about observing a neutron star?
So neutron stars angular size, I think, is still too small.
Aren't there any closer to us?
I think there aren't any that are close enough. And neutron stars mostly emitting in this very narrow jet, which I think, like less than 1/10 of a kilometer across. Neutron stars, a couple kilometers. So it doesn't have this extended emission that goes further out in a disk that you would need to see. But actually we have actually used VLBI data from the Event Horizon Telescope to search for neutron stars in the center of the galaxy. So you can take the same data and just search for pulsars with it. And that would be an incredible, if we found one that was really close to the center of the galaxy, that would be an incredible tool for testing general relativity, because you'd have this precise clock that was moving around in the gravitational field and slowing down and speeding up as it moved around.
Oh, would Cygnus X1 be too small?
Yeah, Cygnus X1 is also too small, unfortunately.
Question?
Yeah.
Are the American National Radio Astronomy Observatories involved with the EHT?
Yes.
The one in New Mexico and the one in West Virginia?
So no, those are both centimeter wavelength observatories and larger, but ALMA is jointly run by NRAO.
Well, what wavelength are you using?
Yes, we're using 1.3 millimeters, but we're hoping to get down to 0.87 millimeters in future years.
Does that require upgrading the equipment on all of those telescopes? Right?
So it doesn't, all of them have receivers that are capable of receiving at 0.87, but it does require upgrading the bandwidth of the recording devices. So I think some of them are at that stage and some of them aren't yet. But anyway, so this is ATMoB, which is run by NRAO.
Is the resolution of your image going to improve with time as you gather more data?
The resolution will not improve with just getting more data unless we add more telescopes. But our ease of reconstructing the image, and in the sense of our resolution as being the features we can trust in the image, that will improve as we get more data and we can look at things that persist. So one thing that's, and you're not trying to talk about, but that's especially complicated in this business is that the stuff around the central black hole is moving very quickly. So it's actually changing over the course of a night, whereas generally you expect astrophysical sources to be nice and stable over long periods of time. The innermost orbit around the black hole is less than 30 minutes in period. So things are working around, and so that actually makes it much more complicated to reconstruct an image, and you might not trust certain features you see just in one night. So if you add up data over a long time, you can hopefully try to average over all of that fine scale stuff that's messing around and then just get the smooth black hole shadow out at the end.
Do you get any gain from the Earth rotating, it's orbiting the sun? Moving the baseline, or is that?
Because you have to observe simultaneously at every site, you can't, you don't get any gain from it moving around the sun, unfortunately.
Okay.
However, people do use the same technique, VLBI, to, actually they do this a lot at Haystack, to measure parallaxes. Because this gives you incredible resolution. If you look at a point source at both sides of the Earth's orbit, you can get parallaxes out to incredible distances. People have done this for, I think there was one recently that just did a parallax of something on the other side of the galactic center for the first time.
Okay, I'm just thinking, because it's, we want you all to have a safe trip back. Andrew will be around if you want to ask any questions afterwards, but I want to thank you, Andrew, for your talk. Maria was setting up the reflections. By the way, Mario is going to be in Quebec City tomorrow talking about light pollutions and spreading the good word again. So again, drive home safely, and we look forward to seeing you next month. And as we've been saying, keep looking up. The meeting is adjourned.